Well, welcome to this afternoon's Aspen Center for Physics public lecture. My name is Gordon Boehm, and I am here representing the center. While my day job is teaching physics in the cornfields at the University of Illinois in Urbana, Illinois, I have been a participant in the center as well as a part-time resident of Aspen for quite a long time. For those of you who are not familiar with the Aspen Center for Physics, let me remark that the center plays an extraordinary role in the lives and progress of the community of physicists. Each summer, normally well over 500 leading scientists from all over the world come here a few weeks at a time to do research on current problems in physics, with virtually no distraction, except of course for the mountains, the music, and other parts of the good life in Aspen. Unfortunately, this year we've had to have a rather limited participation because of COVID constraints. The center is in fact a real summer camp for physicists. Once one becomes altitude adjusted, discussing physics while hiking in the mountains is often surprisingly productive. This series of public lectures is named after Heinz Pagels, who was a longtime participant at the center. Heinz was a professor at Rockefeller University in New York City, a leading figure in particle physics, a distinguished educator, author of popular science books, and president of the International League for Human Rights. He died tragically in a climbing accident on Pyramid Peak here in 1988. Naming the public lecture series after Heinz honors his many contributions to physics and to the world we live in. Let me mention that next week's public talk, July 28, will be given by Peter Onyisi on the flavor of particle physics, which will give us a tour of exotic matter in the microscopic world. And let me also mention that if you'd like to be informed about future events at the center, please email Patty at aspenphys.org, Patty at aspenphys.org, with your email address, or call directly at 970-925-2585. Well, it's a particular pleasure to introduce this afternoon's speaker, Mark Alford. Mark, who's on the faculty of Washington University in St. Louis and current chair of its physics department, is a remarkable theoretical physicist, specializing in understanding the properties of the strongly interacting matter that eventually makes up the atomic nuclei of the real world. He's at Aspen participating in a current research workshop on how astronomical observations can teach us about matter inside neutron stars, stars the size of Aspen, weighing up to twice as much as the sun. Mark grew up in the UK. He majored in physics at Oxford University, but then came to graduate school at Harvard University. After a decade of postdoctoral research in the States, he joined the faculty at Glasgow University in Scotland. A few years later, he moved to St. Louis. For the last 10 years, he's been teaching a course on physics and society, introducing non-science students to the methods of physics and their application to global topics, and at the same time honing his skills at explaining science to non-scientists. Today, Mark will help us understand, in his wonderful style, spooky action at a distance in nature, a fundamental puzzle first realized by Einstein in the mid-30s, and which is now a crucial ingredient in modern applications of physics to the real world, from quantum computing to black holes. Let me say, at the end of the talk, please feel free to ask questions. Just press the raise hand button at the bottom of your screen, and eventually we will call on you. Let me turn the floor over now to Mark. Mark, please.
Okay, thank you very much. Let me share my screen here. Okay, I hope everyone can see that clearly. So thank you very much, Gordon. It's a great honor to be asked to give this public lecture. And so I'm going to talk about this fascinating thing, faster than light, this spooky action at a distance in nature. And there's more. I've got a couple of videos on a YouTube channel, and there's also an article in the American Journal of Physics if you want to go and see more about what I'm going to talk about here now today. So let me start straight in with a thing that many people know, even people who aren't physicists, and that is how Einstein in 1905 introduced us to this universal speed limit, the speed of light. So the claim is that nothing can go faster than light. And the interesting thing is that a short time later, in 1935, Einstein again, this time with Podolsky and Rosen, sort of revisited this topic by pointing out that if information can never go faster than light, then quantum mechanics is not the whole story. They were aiming to show some kind of incompleteness. And the experiment they proposed that could do this was called the Einstein-Podolsky-Rosen experiment. Now, things sat like that for a while. And then in 1964, a physicist called John Bell came on the scene, and he sort of flipped around what Einstein, Podolsky, and Rosen had said to say, if nature behaves as quantum mechanics says, then information can go faster than light. And that follows from the original EPR experiment combined with this inequality that he discovered or invented, the Bell inequality. So my goal for this talk is to explain to a non-specialist audience in totally non-mathematical terms what is going on here, to explain the Einstein-Podolsky-Rosen experiment, the Bell inequality, and how this experiment convinces us that in nature there is some sort of thing going faster than light. All right, so I just want to first show you that these sort of experiments have been done. And by the way, sometimes the name Bohm is added to the end of them because he sort of refined the idea of how to do the experiment. This is an example, a letter in Nature, and the sort of language they have here mentions the Bell inequality and talks about Bell inequality violation. These sort of experiments have been performed many times, and they've confirmed what Bell kind of proposed, expected, which is that indeed his inequality is violated in these experiments. And as I'll show you, that means information is going faster than light. So this has been seen in nature. So let's quickly get an idea of what's going on in one of these experiments. The executive summary, for those of you who may fall off at some point, is, can information really go faster than light? Yes, it can. Is there an experiment? Yes, it's the Einstein-Podolsky-Rosen experiment combined with the Bell inequality. And how does this fit with Einstein's speed limit? Because I started off with that nothing can go faster than light. Well, no thing can go faster than light. What is a thing? So as far as we know, the resolution is no signal can go faster than light. And those Einstein-Podolsky-Rosen experiment results that I'll be explaining to you can be understood in terms of superluminal, faster than light influences that are of a type that can't be used to send a signal. So there is something that goes faster than light, but in a kind of useless way where you can't use it to do what you might want to do, which is send signals faster than light. All right, so I'm first going to show you one slide about how this EPR experiment looks, and then I'm going to translate it into a slightly more sort of folksy idiom. So, but let's start off with something closer to the actual experiment. In the actual experiment, we have a source here which fires out back-to-back photons in a special state, a singlet state, but that doesn't matter too much. It reliably produces these pairs of photons. And all we do is we let each photon go off far, far away to two separate detectors. And when a photon gets close to a detector, the detector has three filters sitting inside it, and it decides at random to plonk down one of those filters in front of the photon. So you can see in this case, photon number one went off to its detector, and when it got close, that detector said, oh, I'm going to deploy filter B. So bang, there's filter B. And photon number two went off to its detector, which decided to deploy filter C. So that happens, the photons arrive, they hit the filters, and they either pass through them or reflect off them. So in this little trial here, the first photon reflected off the filter that it was presented with, which is B, and the second photon went through the filter that it was presented with, which is filter C. So this is, you could write the result as, B minus, meaning the one that got shown a B filter reflected off it, and C plus, the one that got shown a C filter passed through it. Or you could say B no, C yes, or whatever you like. And the detectors are so far apart that these two things happen independently. When this photon is hitting this filter, it doesn't know anything about what's going on over here, where this photon is hitting this filter. Okay, so that's the story in terms of how it's actually done with typically things like photons. But to make it a slightly more human accessible story, I'm going to translate it into a story about people, so that from now on, when we're talking about it, we don't have to talk about photons and filters, we're going to talk in slightly different, more everyday terms. So I'm going to turn pairs of photons into pairs of people. You could think of them as twins if you wanted. And putting a filter in front of a photon is just like asking a person a question. You've got three possible filters, A, B, C, and so we're going to have three possible questions, and we might as well have a theme of, Mexican food or something like that. So the three possible questions, which are also A, B, C, could be like, what kind of food do you like? Do you like avocado? Do you like beef? Do you like cheese? And the photon going through or bouncing off the filter corresponds to a person answering yes or no to a particular question. Okay, so we've set up this, as I said, I hope slightly more relatable version of the EPR experiment where we're doing it with people. And the central claim that we're going to be trying to see how do we prove this, how does the experiment prove this, that there's some faster than light superluminal influence between the photons in a pair translates into these pairs of twins have some sort of superluminal faster than light telepathic connection. So the idea is we're going to do an experiment with these pairs of people, sending them off and asking them questions, and we're going to see how the results convince us that they have some sort of faster than light telepathic connection going on. Okay, so how does this work? Okay, so I have a slide here, but instead of the slide, I'm going to try showing you a little movie. So I'm going to stop sharing here and see if I can instead show you this movie. Okay, let me share again. All right, let's move that into place. All right, so I hope everyone can see that. Does it look okay? All right, so let's fire off the movie. So here are all our twins. We got lots of pairs of twins. We're going to do this experiment many times. Here are our two questioners far away. We send off the twins, one twin to each questioner. And we can zoom in now. What's going on here? The questioner chooses at random what question to answer. So she rolls her dice, and it comes up with a 2, and so she has to decide that means avocado, okay? So that tells her she's going to ask her twin in front of her, do you like avocado? And he gives some answer. He says, yes, I like avocado. Meanwhile, far, far away, the other twin is being asked a question as well. It's important that that's so far away that a light signal couldn't get there in time. So if the first twin wanted to send a signal saying, I was asked about avocado and I said yes, the signal's not going to get there in time, because before the signal gets there, the other questioner has already rolled her dice, which we see she's done over there, and she is asking the twin in front of her a question. In this case, she rolled a 4, so that's going to mean beef, and he says, no, I don't like beef. So she records the answer. I had a twin, I randomly asked him about beef, he said no. Back over here again, the one who was asked about avocado, his questioner, she records that he said yes. And so that's the first trial, that's done. We send the two twins away. We've recorded the answers. No, beef, no on this side, avocado, yes on this side. And so we send them off and we just do the same thing again. So along comes the second pair of twins. They get split up, sent off one to each questioner. And the questioners randomly roll their dice, decide what question to ask. In that case, they happen to both ask about cheese. The twins give their answers. And again, it's important that they're both asked at roughly the same time, so that even if that twin over on the right wanted to tell his fellow twin what he was being asked and what he was going to say, there wouldn't be time for the light signal to get there before the other twin had to answer. So, okay, the second pair of twins has done their job, and we let them go off. And oh yes, so what that tells you is any kind of last-minute coordination would have to be done using signals that go faster than light. That's the point of the setup. So we just do this many, many times. We do it for many pairs of twins. Each one gets asked a random one of the 3 questions, and we end up with a whole bunch of data collected this way, a whole list of what each twin was asked about and what they said. So at the end, we can collect all the data together. Here we are, and here is our EPR data. And somehow this data looks innocent, but actually this data is going to tell us that there's something faster than lightish going on here. Okay, so let me go back to sharing my original screen here. Okay, so this slide was a less enjoyable, I hope, version than the movie. So I hope the movie has made it clear to you what we're doing. So here is the EPR data. It's simulated, of course, obviously, but here is, and we have much more than this. I'm showing you 12 trials here, but you would actually have much more than this to get a statistically significant result. So we have all this data. as I said, it doesn't look that special. It doesn't look like it's going to tell you anything, but actually, as we're going to see, it is going to tell you how these twins have some sort of faster than light telepathy. So let's see how that works. All right, so let's first focus on what happens when randomly it so happens that both questioners ask about the same food. So as I said before, they choose their questions randomly. Each questioner separately rolls dice to decide what to ask, but there's only 3 possible questions. So 1/3 of the time, on average, it'll happen that both twins get asked the same question. So it didn't happen with the first pair, but it did happen with the second pair. It happened down here with the 5th pair and so on, about 1/3 of the time. So we gray out the other ones, and let's just focus on the occasions when they happen to both get asked about the same food. Now you can see here, there's a pretty clear trend, right? If both twins get asked about the same food, they always give the same answer. They always agree. So that's these 4 situations, these 4 trials here. So that's a noticeable regularity in these results. All right, so that says there's something going on here. Now, let's ask, how do they manage to do this? How could a pair of twins arrange things so that they get split up, taken far away from each other, ask questions at random, and when they happen to get asked the same question, they always give the same answer? Well, you can probably think of a couple of ways in which this can happen. In fact, I think there are actually 2. One is that they use some sort of faster than light influence, that they wait until they get close to their respective questioners. And then the first one's, you know, the woman rolls the dice and asks about avocado, and he gets on the faster than light telepathic phone to his friend and says, she's asking me about avocado. I'm going to say, yes, I like it. And he's like, okay, right, I'll do the same thing. And so if you do that, it has to be faster than light because the 2 questioners are asking their questions at the same time, very, very far away from each other. So you need something faster than light, but they could do it that way. That's one way they could coordinate and synchronize and make sure they always agreed when they were asked the same question. But there's a much less exotic possibility. The much less exotic possibility is that they arranged it in advance. That each pair of twins, either they get together before they're sent off and say, okay, let's agree what we're going to do. Avocado is going to be a yes, beef is going to be a yes, you know, cheese is going to be a no. Or it could be they're just built the same, that plan is sort of hardwired into their food preferences, somehow wired into their brain or something like that. Either way, there's some sort of pre-arrangement such that it's locked in what their answers are going to be in advance. So when they get taken far away from each other and asked questions, they automatically agree because they're kind of pre-programmed. Okay, so those are the 2 possibilities. And I want to point out that if the prearranged plan thing is going to work, every pair of twins has to follow a plan because they don't know which pairs of twins are going to end up happening to be both asked the same question, in which case this synchronization is going to be important. So they always have to make a plan and then both follow it if that's going to work. Okay, so these are the 2 ways in which that agreement when asked the same question could work. Now, what our goal here is, we want to show that they aren't doing that more ordinary following a plan thing, and thereby show that they must be using some sort of faster than light influence. So the question now is that, does that tell us anything? You know, can we work that out from what the data that we have? And the very clever thing that John Bell effectively did in this situation is say, let's look at the situations when they were asked, the trials when they were asked different questions. So now we gray out the ones we were looking at before where they both got asked the same question. And now we look at the trials where they each got asked about a different food. Or if you're a physicist and you're remembering with the photons, this would be where the 2 photons got different filters put in front of them. So, okay, this doesn't look like anything special, right? I mean, you know, okay, so the first pair, one was asked about beef and said he didn't like it. The other was asked about avocado, said he did like it. Second one, the third one here, beef was a yes and avocado was a no. And you look at these, they honestly, to me, just superficially, it doesn't look like there's anything interesting going on here. But thanks to Bell, and as we will see, there is a lot going on here, and it is really quite surprising. So what we notice here is 2/3 of the time they get asked different questions. So I'm showing you 12 trials here. So that's 8 of those 12 trials. They got asked different questions. And what you notice is most of the time they give different answers. So this first one, they were asked about different foods and they said different things. One of them liked it and the other one didn't. Same here, asked about different foods. One of them liked it, one of them didn't. This one, they both said the same thing. Asked about different foods, they both said yes. But most of the time, when they're asked about different foods, they give different answers. One says yes and the other says no. And so what we see in our data, and this continues on with the photons with very much larger samples, it continues to be the case, when they're asked different questions, they give the same answer only a quarter of the time. Well, fine. I mean, you know, again, superficially, it doesn't seem like there's anything special about that. But actually, that is shocking. Now, why is that shocking? Well, there's this thing called the Bell inequality, which I'm just going to state right now, and I'll prove it for you on the next slide. And the Bell inequality says if a pair of twins is following a plan, so they've arranged in advance what answers they're going to give, and then when they're asked, they follow the plan, then if they're asked different questions chosen at random, then on average, they should give the same answer, both say yes or both say no, at least a third of the time. That's Bell's inequality, and it's a simple little piece of math that I will prove to you on the next slide. But what we see is our data violates that, right? In the data, when they're asked different questions, they both say the same thing, both yes or both no, only a quarter of the time. And that means they can't be following a plan. There is no way that plan-following twins could only agree a quarter of the time when they're asked different randomly chosen questions. So they aren't following a plan. But in that case, how did they manage to always agree when they were asked the same question? That was the whole reason we thought they were following a plan. We've just knocked out the other way of doing it, so we're left with the first way of doing it. They must be using some sort of superluminal connection because they're not doing it in any preset, hardwired way. So that's basically it. We're done, all right? But we're not done because I haven't told you why Bell's inequality is true. So let's see, why is it true? So here is the simple proof of Bell's inequality. So, okay, we're a pair of twins. We have to make a plan for answering 3 possible yes or no questions. So we make a plan, whatever it might be. Yeah, we're gonna, if she asks us about avocado, we'll say yes. If she asks us about beef, we'll say no, so on, okay? There's not many different types of predetermined plan if you're only pre-planning yes or no answers to 3 questions, right? There's not many possibilities. In fact, there's only 4 basic types of plan. One plan is we're going to say yes to everything. Okay, this is the sort of greedy plan. Okay, then there's another kind of plan where there are 2 things that you're going to like and 1 thing you're not going to like. 1 thing you're not going to like, and that the little example I gave here falls into that category. There are 2 foods that you say you're going to like and 1 you say you're not going to like. Fine. There's another type of plan where there's 1 food that you both agree you're going to like, and the other 2 foods you both agree you're going to say no, you don't like them. And finally, there's this plan, which I call the toddler plan, which is where you say no, you don't like any kind of food. Okay, so here are the 4 types of plan. All right, now, what can happen? Well, suppose you and your twin are asked, you get to the questioners, they roll their dice, they come up with randomly chosen questions, and they happen to be different. Happens 2/3 of the time. Okay, if you both follow the plan as you have to when giving your answers, how likely is it that you'll both end up giving the same answer to the 2 questions you're asked? Okay, well, we can just look at it. So let's take the 3 yeses plan. The 3 yeses plan, any 2 questions that you're asked, you'll always give the same answer to both of them, right? And the same is true with the 3 no's plan. Any 2 questions you're asked, you'll always give the same answer to both of them. Let's look at the other 2 classes of plan. The 2 yeses and a no plan, well, there's 1 pair of questions you could be asked where you'll both say the same thing, but the other 2 pairs, you'll give different answers. And the same is true with the 2 no's and a yes plan. There's 1 pair of questions different questions that you could be asked where you'll both say the same thing. But otherwise, if you're asked this pair or this pair, you'll end up saying different things. So in these 2 cases, since the questions are chosen at random, 1/3 of the time, you'll end up saying the same answer when you're asked different questions. These ones at the edge here, you'll always give the same answer when you're asked different questions. So at least 1/3 of the time, if you choose any plan, doesn't matter what plan you choose, at least 1/3 of the time, on average, if you're asked 2 different questions, you're going to give the same answer, okay? All right, so that proves Bell's inequality. If your questions are chosen randomly, and you're following a plan when you give your answers, the 2 of you are following a plan, then at least 1/3 of the time, you ought to give the same answer to both questions. But as we saw in the data, when they're asked different questions, they only give the same answer a quarter of the time. There is no way of doing that if you're following plans. Now, each pair of twins doesn't have to choose the same plan as any other pair. It doesn't matter, right? Each pair of twins can make their own plan, but it doesn't matter. Any kind of plan following, as you just saw in the list of plans, is going to lead to you giving the same answer when asked different questions at least a third of the time. But what we observe is different from that. We observe that's only happening a quarter of the time. So they can't be following a predetermined plan. So the summary here is that there is some sort of superluminal influence. In order to always agree on the occasions when they were asked the same question, each pair of twins would have to either follow a predetermined plan or use faster than light communication. We've looked at the pattern of their answers when they were asked different questions. We've seen that it violates the Bell inequality. They can't be following a plan. They must be using superluminal communication. Now, how would they be using it? There's a couple of different ways, which we can just mention because it's maybe interesting to flesh it out a bit and get a sense of what's going on. One way I mentioned earlier on. So one way would be they don't bother with any kind of planning. They get taken far away from each other. And when one gets asked a question, they superluminally communicate to the other what question they were asked and what they're going to say. And so that allows them to coordinate. Another possible way they could do it is they could make a plan and have the plan in mind. And then if it turns out that they get asked different questions, they can sort of discoordinate, right? If they got asked different questions, they can superluminally communicate, realize they've been asked different questions and say, okay, we're not going to follow the plan then, right? That's another way of doing it. You can probably think up other little scenarios for twins. But whatever you do, you're going to have some kind of faster than light component, because the other way of doing it, the pre-programmed, predetermined way of doing it, will not give the pattern of answers that we saw in the data. Okay, so now, at the very beginning, I talked about Einstein a little bit and his theory of relativity. So how does this cohere with relativity and the well-known fact that nothing can go faster than light? Well, if you look at it closely, what's really forbidden is superluminal signaling. If you assume that relativity is true and that we have free will, then if you can send a signal faster than light, then you can send a message into the past. And if you can send a message into the past, this leads to causal paradoxes. People sometimes call this the grandfather paradox, where you send a message into the past that distracts your grandfather from meeting your grandmother and ensures that you don't exist. And then how could you be there to send the message into the past? So the really troublesome thing is superluminal signaling. Now, signaling requires two things. Yes, it requires superluminal transfer of information, but it also requires you to be able to control the information that is transferred. That's the definition of a signal. It's where you decide what information you're going to send. Now, we're seeing some sort of superluminal transfer of information in this EPR experiment, and that's actually okay as long as the information that's sent is uncontrollable. Now, admittedly, this is a bit weird because controllability is not the sort of thing you normally talk about in physics. You talk about symmetries and things like that, but you don't normally talk about controllability. It's already assumes some sort of high-level concepts, right? But even so, okay, let's allow ourselves to do it. If you don't get to control the information that goes faster than light, if it's kind of nature decides for itself, oh, well, I'm going to move this information from here to here faster than light, but it's whatever information I decided to send, you have no influence over it, then that doesn't constitute superluminal signaling. It doesn't create causal paradoxes. And that is roughly what we think is going on here. So the question is, how do we avoid superluminal signaling? How can we have laws of nature? Somehow, the laws of nature allow for this faster than light EPR information transfer. We've just seen it in an experiment, but they do not allow causal loops and paradoxes. So they somehow the laws of physics ensure that the information is uncontrollable. How is this accomplished? Well, one example is textbook standard quantum mechanics. So textbook standard quantum mechanics accounts for all this. How? Well, it's got the collapse of the wave function in it, which is instantaneous over all of space. The collapse of the wave function is superluminal. So actually, that is a faster than light component in quantum mechanics, which allows quantum mechanics to account correctly for the outcome of the EPR experiments. But another component of quantum mechanics is that when the wave function collapses, there is an indeterministic choice of what state it'll collapse into, what result a measurement will give. You don't get to choose that, so to speak, nature chooses. And that's the information that gets transferred superluminally from one place to the other, from one twin to the other, or if you're a physicist and you still remember where we started, from one photon measurement to another photon measurement. Whether the photon bounced off or not, you don't get to control that. It just does one or the other, and you don't control it. So the result is the quantum mechanics does exactly what we want. It has a superluminal component in it that allows this information to be moved faster than light, but the information is indeterministically chosen, sort of by nature, so it doesn't allow you to send a signal, so you can't assassinate your grandfather. Now, so you could look at this and say, well, okay, does that mean we always need to have indeterminism in nature in order to have our superluminal stuff not sort of infect the controllable sector of our theory and thereby allow for sending signals faster than light? And actually, that's not necessarily the case. In a deterministic theory, you do need some special mechanism to keep the superluminalness away from people being able to control it. But there are other theories, like there's this theory called Bohmian mechanics, which has a quantum equilibrium hypothesis, which is designed to do exactly that. Now, I have to say, I don't know really anything about Bohmian mechanics. I'm just telling you that there are proposals out there of deterministic theories. Bohmian mechanics is explicitly superluminal. It has faster than light stuff in it in order to account for the EPR experiments, but it also has this sort of special feature in it to ensure that you can't send signals with its faster than light phenomenon, even though it's a deterministic theory. Okay, so I think you've suffered enough at this point. So I'm going to sort of head towards wrapping up here, I think. I'm going to mention a few things that some of you might be interested in. What I laid out for you here was obviously as simple as I could possibly make it. And that meant that I glossed over a few things. So let me mention a couple of background assumptions. One is I made this assumption that's often called macro realism, which is that each experiment has a unique outcome. And that is what we see in nature. You do experiments, you get answers. But still, it's an assumption. Another assumption is random choices. I assumed that our two questioners or experimenters could throw dice independently of each other and independently randomly choose what question to ask or what to measure. And that was uncorrelated with what the particle states or what the plan of the twin in front of them was, independent of what the other experimenter was doing. I assumed that it was possible to accomplish that. And then there's another assumption, which is that I assumed that the detectors were perfect, that there was no errors, or that some twins didn't just wander off and refuse to go to the questioners, or talk in a language the questioners couldn't understand. That translates into sometimes the detector glitches and misses a photon. That inefficiency loophole was actually closed. That paper I showed you earlier on, at the very beginning, that Nature paper, its claim to fame was that it closed the inefficiency loophole. It used very efficient detectors such that detector inefficiency couldn't possibly account for the violation of Bell's inequality, the superluminal phenomenon that was seen there. So who would disagree with some of these things? Well, there's the many worlds interpretation of quantum mechanics. People who follow the many worlds interpretation would deny macro realism. They would say that experiments don't yield unique outcomes, in which case they need to explain how you get probabilities out. Because it's not so obvious how you get probabilities out if all you have is a wave function evolving according to Schrodinger's equation. There's no probabilities in there. So that's the challenge for non-macro realistic theories like many worlds. There's another idea called superdeterminism. Superdeterminism says that you can't make your experimenters do random choice of what to ask or what to measure independent of each other. It's all super determined in advance and set up in just such a way to make it look as if something's going faster than light, but really it was all set up in advance in some kind of conspiracy. And then finally, there's a thing called retrocausality, which is the suggestion that the experimenter's choices can affect how the particles were prepared. So that does seem like it's going to lead to causal paradoxes, but I'm mentioning it just because you can find it out there in the world. And some people say that. So actually, I think I'm pretty much at the end here. So I'm just going to talk about a few places one could take this in the future. You can try and close the random choices loophole, at least as best you can. You have to make some assumptions, of course, about the universe we live in. One way of doing it is to say each experimenter will use a random number generator that is outside the other experimenter's past light cone. So you have to somehow gather data like from the cosmic microwave background or something in such a way that the other experimenter can't see it. This is sort of assuming things don't go faster than light in order to prove that things do go faster than light, but okay. And there's papers on that. If you believe in macrorealism, then there's this very interesting sort of weirdness that we think that that quantum mechanics is compatible with special relativity in the sense that you can't send signals faster than light. But our textbook formulation of quantum mechanics has this superluminal thing in it, wave function collapse, instantaneous across the whole universe. So one thing that people have looked for is there a way of formulating quantum mechanics so that it's blatantly compatible with relativity? It doesn't even look like it has anything that violates relativity. And that the word for that is Lorentz invariant in physics jargon. So one thing is, can you find a Lorentz invariant version of wave function collapse so that quantum mechanics doesn't look like it violates relativity? Now, people who don't believe in macrorealism, people who believe in many worlds, the goal for them would be, okay, can you have a Lorentz invariant many worlds type quantum mechanics that leads to the same predictions as textbook quantum mechanics? And you get probabilities out. How do you get the probabilities out? And there's a whole bunch of literature on that of people talking about how they can do it and whether it's easy or not. And finally, another direction that some people are interested in, which I alluded to earlier, is if you don't like the indeterminism of quantum mechanics, can you come up with some sort of preferably special relativity compatible Lorentz invariant deterministic alternative theory, such as a version of Bohmian mechanics that you can make Lorentz invariant? And then you'd have something that was compatible with relativity, deterministic, and had some sort of mechanism in it so that its faster than light component couldn't be used to send signals. So there's all sorts of exotic directions in which you can go from this simple but intriguing observation about nature. So, okay, I think I'm going to draw a line here and say that's it.
Mark, thank you very, very much. Let me call for questions now from the audience and remind you to do this. Simply press the raise hand button. And the first name pops up is Connor Hoffman.
Hi. Very nice talk. Thank you. When you're talking about the 1/4 probability thing, are you saying every single time you do this experiment or you get a large enough data set, it'll be a fourth at the time, or just in this circumstance?
No, I'm saying that whenever you do this, you gather a lot of data, and you'll always find that with these pairs of twins or these pairs of photons prepared and drawn from the appropriate population, you keep doing more and more and more and more of them, and on average, when they're asked different questions, they'll only give the same answer a quarter of the time. I think you have some background noise there.
And/or gun shops that are
That's not me. Thank you.
So we're going to do major investigations and shut those guys down and put some of them in jail for what they're doing, selling.
Sounds like, okay, need to mute somebody. Okay, yes. Gordon, you're the MC here.
Okay. I'm looking for more hands raised. Okay, I'm looking for more hands raised. I don't see any at the moment. Let me ask Mark. In my introduction to you, I mentioned that the EPR, Einstein-Podolsky-Rosen concept was very important in modern physics. Could you say a word about how that happens?
Sure. Well, so another word for what's going on here is entanglement.
Yeah.
That the two particles are entangled with each other, and that's this superluminal correlation between them is another way of saying that they're entangled. And entanglement is exactly the mechanism behind quantum computers that people hope will allow us to process data and solve problems that have up to now been either impossible or, well, exponentially difficult to solve. The hope is that using the power of a quantum computer that can store energy in quantum states instead of classical states and use that entanglement between them, that you can crack previously uncrackable problems.
Thank you. Bert Sharp? Bert Sharp, you have a question? Your hand is up. No.
This is Nick. I don't see a hand, but can I ask a question?
Yes, sure.
Yeah, hello. I'm trying to get myself unmuted. This is Bert Sharp. And Mark,
yes.
Question for you. What is the theoretical characteristic of the energy that is carrying this information between these subjects?
Right. So it's not going to be energy. If energy traveled faster, let me go down here a bit. If energy traveled faster than light, that would basically be signaling. That would be moving something controllable from one place to another. If you look, I've been quite sort of cautious about the language I've used, and I've said things like superluminal transfer of information. It's not even, you can't even tell which way it goes, because if something goes faster than light, then in different reference frames, you can see it going either way. So in one reference frame, it looks like it goes from twin 1 to twin 2, but if you can go to a different reference frame where it looks like it goes from twin 2 to twin 1. So you can't even really say which direction this information is going in. And that's why I used rather sort of weaselly language like transfer of information. I'm trying to, not say that it's a communicating signal being sent from A to B. It's some sort of faster than light connection or faster than light something, I don't know. It's quantum entanglement. It's very weird.
Very good. Good.
Hello.
Yes.
It's always helped me to understand this. Instead of superluminal, wherever you're using the word superluminal, would you accept that at an earlier time, these two particles, or in your case, two people, had worked together and therefore shared a common wave function that they've therefore continued to share as they fly apart, and just to use that instead of the superluminal at the places in your discussion that you've used it?
No, that's exactly what we've sort of shown is not adequate, right? The wave function does not determine what their answers are going to be. And the two choices for how to do it, if I go back, are either they do something faster than light, or they follow a prearranged plan. But a prearranged plan only works if it prearranges. If all they have is a wave function, then when question time comes, they could collapse and give different answers, right? One of them collapses, it's the wave function and says, yes, I like cheese, and the other's asked about cheese too, and collapses independently and says, no, I don't like cheese. Then they won't be giving the same answer. So you need some sort of faster than light connection to ensure that the wave function collapses onto the same answer for both of
them. Thank you.
Very good.
Mark, I have one more question for you. Is that faster than light quantum?
Is it what?
Is it quantized that faster than light? For example, if it was at two ends of the universe, would it be as rapid?
Well, We don't know, of course, because we haven't done that experiment, but the experiments that we've done are consistent with it being instantaneous. And quantum mechanics at least says it's instantaneous. Now, is it possible that in the future we might do measurements that see something different from that? Yes, of course. But all we can see at this point is that, you know, something like that Hansen paper I showed at the beginning, they do the measurements in a way that they're far enough apart and it's close enough in time that something faster than light has to connect in some way. But how much faster than light, I don't know.
Okay, thanks.
Okay. But
yeah.
Let me ask, if instantaneous means at the same time for both people, then as seen from a moving train, they'll be at different times. So
right, that's what I was alluding to when I said that you can't tell which way it goes.
Yeah, exactly.
Right, you know, it's instantaneous as far as we can tell. It's space-like, okay? It's in physics jargon.
Yeah.
And faster than light in this case means you can't even tell whether it goes from A to B or B to A. Okay. It's a bit hard to say what it's doing in any sort of normal language.
Very good. Okay. JFN.
Yes, thanks. That's me. It's Julio Navarro. Thanks, Mark. A wonderful, you know, so simple description of something I've been trying to teach my students many times and never always failed to communicate clearly. Okay, so I had always a question. You know, there is a special set of twins, using your analogy, for which these inequalities hold, right? The entangled twins, let's call them that way, right? It's not just any random.
Yeah, these twins. Okay, these twins are all entangled. The assumption. So in the original experiment, the photons are produced in a spin singlet state, and that's how come when they're given the same filter, they give the same answer. Right. And so these twins have some special property, and we're just teasing that special property out. This population of twins, I should say. So I'm just showing how a population of twins could exhibit this, and they're just an analogy for a population of photons exhibiting this special feature.
So is one saying then that this transfer of information faster than light only happens for a very particular, you know, arrangement in nature, and it's not a common feature of
right? Well, it's common in the sense that entanglement is common, but yes, it has to be two photons that are entangled. They are produced in a spin singlet state with a wave function that you know what the spin singlet wave function is. Mm-hmm. Yeah, if you produce them in uncorrelated states, they won't violate Bell's inequality.
Yeah. Right. But when you do the statistics, I guess the question is, I mean, this is always a statistical thing. You need to do millions of these measurements to do it. Is it possible that we're somehow missing the ones that would give us, you know, that would solve the Bell's inequality, that somehow those we cannot be measured? Or I guess that goes under your
yes,
perfect.
Exactly. That's the perfect detector's inefficiency loophole, which Henson et al. Claim to have closed by capturing basically all the photons that they create.
Okay, so they basically count them all, and there's no.
That's the claim. Yeah.
Okay, wonderful. Thank you very much.
Connor Hoffman, do you still have a question? Your hand is still up.
Yes, I do.
Okay.
So this may be a very lay question, but is there a simple explanation for what a wave function is, or like an easier way to think about what it is?
You're asking for the simple explanation of quantum mechanics? I'm not sure there is. I mean, it's a function that tells you what is likely to happen when you do measurements. Okay, so it's telling you something about what's going to happen, but not everything about what's going to happen. And it leaves this sort of open randomness for what's actually going to happen to be decided later.
Okay, so it's like a mathematical model then for representing what happens between two particles, or something kind of like that?
Well, in a sense, all of physics is what you just said. It's all mathematical models. So this is, of course, a mathematical model, yes.
Okay, kind of a simplification then.
We suspect that all our physical models are simplifications of you know, future better models.
Okay.
Good. Yeah.
Any other questions?
I don't see any more questions. No, no hands
Yes,
raised.
I have a question.
Okay, well, at this point, let me thank Mark again for a wonderful, charming presentation of the Einstein-Rosen-Podolsky puzzle. And we look forward to seeing you all next week, same time, 5:30, next Thursday, for Peter Onyishi's talk on particles. Thank you all very, very much. Good evening. Good evening, all.